Good morning, everybody. It's my great pleasure to participate in this great event. Sadly, I'm not around, but I hope the next time I will be, and that the whole situation on health and travel restrictions is then something of the past. What I would like to talk to you about is basically relatively conventional steel making on the blast furnace and the basic oxygen furnace route, and how you can work on that and use industrial symbiosis and CO2 storage to reduce the CO2 emissions overall. So what do we think then about the CO2 sources that you can think of if you're talking about industrial symbiosis and CO2 utilization? You can think, of course, of all kinds of emissions, and I put here some like industrial emissions, biomass gasifications, of course, also very important to carbon feedstock biofuel production, where there is always an excess in carbon, but also direct air capture you can use. And what can you make then from that carbon is all kind of value-added chemicals, from urea as a fertilizer, as already been mentioned before, but also methanol. And methanol is, of course, a very important chemical that is, can be considered as a liquid syngas, and you can use it as a fuel. A more advanced one is dimethyl ether. And if we look then at what is CO2 use, CO2 utilization, it's basically industrial symbiosis. What you have to do is you have to combine various markets and various technologies from different sources coming. So what I will be focusing on today is industrial emissions and how we can transform that into urea and methanol. And as said, we will focus on steel industry and especially the BF-BOF route. The first project I would like to talk about, the first effort that we did, was using blast furnace gas and transform that into methanol as a marine fuel. We have been working on this in recent years, and we have demonstrated that you can actually make methanol. We produce in total 23 cubic meters of methanol, and use that in the Stena Germanica, a ferry line operated by Stena. And as you can see, we work here in a large consortium. I have depicted here a few, Swerim, which is basically located in the north of Sweden next to the SAB steel plant. There's a location of we do our research, demonstration work. We work together with CRI from Iceland, and we work with Stena as a shipping company. What we also, what I will pass some more work on is how we are progressing now, and that's basically valorizing basic oxygen furnace gas into ammonia and urea. And the whole thought behind that is that these gases contain energy, and you want to convert the energy in those gases into something valuable. And normally it's being done, it's be converted into electricity and heat. But we are working towards value-added chemicals to increase the profitability of the whole process. So if we look at the iron steel and in connection with ammonia or urea within Europe, you see there are massive economic impacts. There are huge environmental impacts as well, and surprisingly enough, per ton of product, they have similar CO2 emissions. They are widespread in Europe, and both are quite strongly imported as well. For ammonia, for instance, 60% is only produced locally. And well, I think the whole impact we already been discussed it. And it's also important how to see how that continues in the future, but also how to maintain it, because the demand will be here. So if we step up, move into a little bit more technological approach, basically, the key technology in here is CWAX technology that treats the BOF gas. And basically what it does, in one step, it converts your feed gas, so your BOF gas, into a hydrogen and nitrogen stream and into CO2. So the CO is converted into CO2, and at the same time, you produce hydrogen. We move that to the ammonia synthesis unit, the hydrogen and nitrogen, and an electrolyzer to add some hydrogen when needed, depending on the exact composition of your base oxygen furnace gas. Of course, the CO2 has to be tuned, And then if you have synthesized ammonia and you have your purified tuned CO2, you can go to urea synthesis and have your valuable product. At the same time, you create storage-ready CO2. And I will show later on that storage-ready CO2 becomes available free of costs. So the key technology in here is, as said, the CWEX technology, our absorption enhanced Watercase shift. And for that, we built a reactor in Sweden of the size of about 60 centimeters in diameter and 10 meters tall to do the first experiments. But what is that? What is that kind of technology? Well, it's a absorption enhanced Watercase shift. And in there, we basically convert CO together with the add of steam into CO2 and hydrogen. And you do that then in a pressure swing manner. So you feed it, you let the CO2 absorb at the sorbent material and until that becomes saturated. At the start, you get then the product of hydrogen and nitrogen coming out of your system. And when the sorbent is full, you go into a rinse step and you do pressure equalizations and you do the regeneration. And you use steam for that. And this technology is unique as it uses a very limited amount of energy, a low steam consumption, and it is much more efficient than amine-based systems. You can apply this approach in various markets. And as said, we have demonstrated it at TRL 6 on real furnace gas in the Stepwise Horizon 2020 project and also in the Fresme that I mentioned before. And in total, we have been operating this now for about 9 months. When we go to ammonia, I will look at how the economics play out. You know, and here we compare in blue the reference case, so that's the natural gas-based ammonia production, and I compare that with the price that we come up with. And if you look at the thick blue line and the thick red line, those are the central values that we estimated, and you see that even it's lower our estimates than conventional synthesis. But there's of course some error margins around it. Local situations are very important in that. But the bottom line is the urea can pay for the capture technology, and you know you get the storage-ready CO2 as site product for free. So how does it then in a life cycle analysis? What kind of advantages does it give it to you? The reference case on the left-hand side, that's just common practice as we do now. So you have the gray area, which is basically the electricity production from BOF, and the orange, that is the gas processing and synthesis from the ammonia part. If we now go to our approach, there is the light blue, which is the excess of CO2 that's being vented in this first scenario, and the dark blue is the electricity replacement that has to be done because we still have to make the electricity, and we assume it's electricity as it is in the Dutch grid system at the moment. In orange, you see the gas processing as well. So you see if you just implement it, you get a reduction of about 13%. However, if you go and also store the CO2 that becomes free of charge available and you have a storage nearby, then you can reduce it to 70%. And the remaining CO2 footprint is basically electricity, because the dark blue on the right-hand side you see is electricity replacement. You can reduce that. And also CO2 transport and storage is also very much electricity based. So even if you can reduce that, then you see that you can lower your CO2 emissions by about 90%. So this is, we have been working that out on paper quite extensively, as you saw, and now we are in the phase of demonstrating this in the real life. So again, we're going to Sweden, in the north of Sweden. We go and expand our current installations to a multi-column installation. And this is a big demonstration that we're going to use, where we're going to produce about 5 tons of ammonia per day, and we're going to operate it for 4 or 5 months. So in total, 3 campaigns we are going to do, and that will lead to a TRL 7 gas treatment demonstration. And we're really going to make ammonia. So again, we're going to demonstrate that you can make your valuable components from steel off gases. So coming towards the end, the bottom line is cost-effective CO2 emissions reduction are possible, and the CWEX technology is key on that. And to answer one of the comments before, we are the technology owners, and we are happy to license that to firms and especially OEMs, so it can become available worldwide. Luckily, we're not doing that on our own. We have a wide array of companies and organizations around it. We work together very closely with all kinds of steel companies. In the left top hand, in the left bottom, you see all kinds of supply companies and end users, and you see also OEMs on the right bottom, and all kinds of the universities and other knowledge institutes. So we work in a whole ecosystem of knowledge and innovation together. So a big thank you for them. But we cannot do that without funding, and we have been very successful in recent years in raising funds for our approaches in Horizon 2020 projects. And here you see I mentioned 4 projects that have been running in recent years, or that they are still running. And of course, we're looking forward, because we are ready for 100 kiloton per year of CO2 capture facility, and we are very much inviting parties to join us on that excursion, and we look very much forward to doing that and to make an impact. So with that, I come to the end of my presentation. I thank you all for the attention, and I look forward to hearing your questions, and of course to meet you in live, hopefully next year, for instance, at the next forum. Thank you all.